Welcome, everyone. For today's prep, we're going to look at a special type of improper integral, which we call a P-form improper integral. And we're going to see when these are convergent and when they're divergent. So first of all, well, what are these P-form improper integrals? Well, it's just a special type where we're integrating the function 1 over x raised to the power p. And the way we've stated this result, we're going to be integrating that function from 1 to infinity. And we're going to be focused on what this exponent actually is. So depending on this exponent, p, that tells us when our improper integral converges and when it diverges. So we're actually going to prove this result. We're going to actually calculate our improper integral over a few different cases. So it converges when p is greater than 1. And then it diverges when p is less than or equal to 1. And, this is going to be a fun exercise. We know how to do improper integrals, so we're going to be able to prove this result. But this is going to be particularly useful when we get to series and sequences a little bit later on in the course, especially series. So we have all the machinery now to actually prove this result, and then we're going to come back and use this result once we get to sequences and series. So kind of flag this, we're going to come back to it. And why are there different cases here? Well, it comes down to our antiderivative, the antiderivative of this function. So that's what we're going to look at first. We're going to look at this antiderivative. So we have this function 1 over x to the power p. And normally, power rule would work. Power rule is going to do most of the heavy lifting here, with one exception. So when p is equal to 1, we can't use power rule. So that's kind of where the first case gets broken off. So we're going to split this up into kind of two cases right now, when p is equal to 1 and when p doesn't equal 1. So when p doesn't equal 1, well, then we could just use our regular power rule. So we could rewrite this with a negative exponent, x raised to the negative p, and then we can just do when we integrate, we just do our regular power rule. So we add 1 to the exponent, so we get x raised to the negative p plus 1, and then we take that new exponent and flip it and put it in front. Okay. So just regular power rule there. Well, what happens if p is equal to 1? Well, when p is equal to 1, we end up with the special case for our function of 1 over x. And this is the case where power rule doesn't work. And when we integrate, we end up with natural log. Okay. So right now there's two cases, when p is equal to 1 and when p doesn't equal 1. Well, if we look at this exponent, we can break this down into two further cases. So this exponent is kind of important for how we're going to consider some of the improper integral calculations. So we're going to break this down into two separate conditions, when p is greater than 1 and when p is less than 1. So what happens in the case when p is greater than 1, this exponent, which is negative p plus 1, that exponent is negative. So if p is greater than 1, so something like 2, we end up with negative 2 plus 1. We end up with a negative exponent. Now in the other case, if p is less than 1, so maybe something like 0.5, well, in this case, the exponent that we end up with in our antiderivative is positive. So that change is actually going to be important. So if we pick if our p-value is like 1/2 or 0.5, we would end up with negative 0.5 plus 1, and that's positive 0.5. So what we're going to do is we're going to prove this result for the case when p is greater than 1. So we're in this realm right here where our exponent, when we get the antiderivative, our exponent's going to be negative. So let's start this off. So we're going to prove this. So we're going to calculate our improper integral. First step for any improper integral, rewrite it as a limit. So we're going to kind of peel that infinity off of our integral sign. We're going to sneak up on it with a limit. So we're going to do the integral from 1 to b, and then calculate the limit as b approaches infinity. And then our antiderivative here, or our function is 1 over x to the p. All right. So we get the antiderivative, and when we did that above, we used the power rule, and we got x raised to the negative p plus 1 with 1 over negative p plus 1 in front. So that's what we got for our antiderivative in that case. And then we're going to evaluate this from x equals 1 to x equals b. Now, before we do that evaluation, this exponent here, this negative p plus 1, we said it was negative. So we're in this case when p is greater than 1. So our exponent there is negative. So whenever we have a negative exponent, it's usually helpful to rewrite that back as a fraction. So we're going to rewrite this power of x. Rather than having a negative exponent, we're going to write it as a fraction. So how is this going to look? Well, we still have our 1 over negative p plus 1 out in front. And then when we write this as a fraction, we're going to get 1 over x. But then when we write it as a fraction, we're just going to flip the order of the subtraction here. So almost like we're just going to do a double negative. So we end up with p minus 1. And now p minus 1, we've just kind of switched the order of the subtraction. So now p minus 1 this is a positive exponent. So we've gone from having a negative exponent, where it's x raised to a negative exponent, and now we've just rewritten this function as 1 over x, but now this exponent is positive. And again, it's just the reason why we do this, it's just helpful to have, rather than dealing with a negative exponent, it's helpful to deal with a fraction instead. All right, so now we just evaluate. So top number gets plugged in first. And when we evaluate this 1 over negative p plus 1, where p is just a constant. So this is just a constant multiple here. So if I wanted to, I could move this out in front of the limit. So when we do it, or another way to think of that is I could just evaluate this variable part and have this constant multiple multiply the whole thing. So 1 over negative p plus 1 times, and then let's do our evaluation. So top number goes in first, so we get 1 over b raised to the p minus 1. And then when I plug in the lower bound, I end up with 1 over 1 raised to the p minus 1. And then I subtract. And this power of 1 is just going to simplify to just 1. And then this fraction here, we're just about ready to do the limit. So we want to think about what happens as b approaches infinity. So we want to start to think about what happens to each of these terms as b is approaching infinity. Well, first of all, this fraction in front, there's no b's. P is just a constant, so this whole thing is just a constant. Same thing with this over here. So both of these are just constants. So they're just going to stay exactly the same. Really, the only thing with a b in it is this fraction here. And having it written as a fraction is just going to help us recognize that this is a c over infinity form. So the numerator is a constant, and then our denominator is getting really big. So this goes to 0. So when we actually calculate the limit, we end up with 1 over negative p plus 1 times 0 minus 1. And if we simplify, we can take this negative. We can either put it into the numerator here, or I can take this negative 1 and multiply it into the denominator. And if I do it that way, I end up with 1 over 1 minus p. No. 1 over p minus 1. There we go. So I'm just distributing the negative 1 into that denominator. So I'm multiplying it with the negative p, so it becomes positive, and then multiplying it with the plus 1, so that becomes negative. And so what we get here, again, p is just a number, so we end up with this, well, number as our value. So the fact that we actually get a number for our improper integral tells us that it is convergent. So we proved it for this case. So in class, we're going to look at the other cases. And actually, I might have you do the case for p equals 1. I might have you try this one as a prep problem. All right, so let's just look at one example where we get to apply this. So let's look at this integral, this improper integral for 1 to infinity of the function 1 over x squared. So when we look at this, we want to recognize this as a p-form improper integral. And we want to state the p-value. So in this case, the p-value is the exponent on our x term when it's written as a fraction like this. So the p-value here is 2. Even though technically the exponent on the x here is negative 2, we're looking at it when it's written as a fraction. So the p-value here is 2. And because 2 is greater than 1, what this means is this improper integral is convergent. So we're able to kind of quickly tell when these special types of improper integrals are going to be convergent or divergent. And so once we prove the other part of the results, namely for the case when p is less than 1 and when p is equal to 1, we'll look at example 2, where we have this function 1 over square root x. But for right now, we'll stop there, and we'll finish this up in class. So we'll see you then. Bye-bye.